Hello student, today we're going to solve a problem on curvilinear motion, and yes, the problem will involve a plane. So let's see the problem. So the learning objective of today's problem is how can we determine the velocity and acceleration if we know the trajectory, that means the path of a projectile or plane, and given a velocity component of that projectile. So seeing these images, we can tell that the problems may involve a plane and a radar and a radar scan. So let's see the problem. The problem says a signal is received at a radar station that a plane is following a trajectory of this y equals to 0.005 x to the power cube plus 1000. It is measured that the plane is descending with a constant downward velocity of 25 meter per second. Determine the velocity, acceleration, and time required to reach at the radar station when the current altitude is 15,000 meter. So before we solve the problem, we know that if we follow some steps, it will be easier for us to solve the problem. First, we would like to find what is known and unknown, so what is given. So we know the trajectory of the plane is given, which is y equals to 0.005 x cubed plus 1000, and the downward component of the velocity, so it's downward, so it's in y direction, is given 25 meter per second. And let's see if anything is given. And the current altitude is y, which is 15,000 meter. Okay, so these are the knowns. So what are the unknowns? What we are looking for? It says determine the velocity, meaning the magnitude of the velocity. We don't know. The acceleration, the magnitude of acceleration, and time required to reach at the radar station from the current position. So to clearly understand the problem, let's draw a diagram, which we can say this is x direction and this is y, which is amplitude, and our radar station is right here at the origin. So now our current position of the plane is here. That's a plane. Okay, and it is following a path which is given. So from the equation here, we see if we put x equals to 0, we get y equals to 1000, meaning when the plane reach at the radar station, it will be at least 1000 meter above the radar station. And since it follows a curve, we assume this follows this curve, and this is the path the plane is following, and this curve is the same equation as this one. So now let's start solving the problem. So which one would be easier to solve first? So we know this is the time, and currently the plane is at 15,000 meter. Since the downward velocity is constant, we can use the formula, which is distance s in y direction is same as velocity in y direction and time. So time, we can get s, the distance, so it will be 15,000 minus 1,000 here. So we can get 15,000 minus 1,000 divided by the velocity, constant velocity 25, which gives us 9 point approximately 3 minute which is 560 second. So the time required for the plane to reach at top of the radar station when following this trajectory, this path, is time equals to 560 second. So we solved the first one. Now we can also see how far the plane is at current position, that is x, in x direction, horizontal direction, and we can find it by using the path given. So if we put y equals to 15,000, we can find x. For example, 15,000 equals to 0.005 x cubed plus 1,000. So if we solve this, we can get x equals to 140.95 meter. So this is how much distance away the plane is in x direction. So this will use letter. So we got one answer. So now let's solve for velocity. Velocity v, which is a vector, which will have two components in x direction and in y direction, and we can get the, so it will be the magnitude, I'm sorry, this will be the magnitude, and the velocity in vector form would be vxi, let's say x direction, and vyj in y direction. So now to solve for velocity, we have to see what is given. So since the velocity in y direction vy is given, we'll see can we connect this given value with some other variables, so we can start from there. So we know velocity in y direction could be written as derivative of y in y direction, distance y, which is a function of x, dt. So if we take derivative of y with respect to time, we can get the vy component. Now we see that the y is a function of x, but we are taking derivative with respect to t. So what we have to do, if we simplify, we can take derivative of y, which is a function of x, which with respect to x, and then we have to balance with dx over dt. Now this part dx over dt, actually the velocity component in x direction, because x distance with respect to time, so that vx. So this gives us vy equals to this part that we have to take derivative of the y equation, which is multiplied by vx. So if we get the equation, we see vy will be equals to, if we take the derivative of y component, we see 0.005, because that's constant, and for x cube we'll get 3x squared, and then we had the multiplication of vx from previous slide, and for the 1000 it's constant, so it will have 0, and it will be multiplied with vx, which is which will be 0 again. So this term goes to 0, and we'll have this vy equals to this equation. We can call it equation 1. So now we know that the vy at that position, when at 15,000 feet altitude, it is having a downward velocity of 25 meter per second, and we have on this side 0.005 3x squared vx. Now if we can plug the value of x that we just figured out in previous slide, which is 140.95 here, then we can get the value of x. So if we plug x equals to 140.95, if we plug it here, and we can solve for vx. So if we solve for v, we get vx equals to 0.084 meter per second. Well, that tells us that it's most likely the plane is having a dive almost vertically. That's why the vy is very larger than vx. We'll get a negative sign, meaning that plane is moving in the negative direction of the coordinate. Since we have the vx and vy both, we can get the magnitude of velocity v by taking minus 0.084 whole square plus we had a vy of 25, so that's whole square, and so we will get, so we get 25.00014 meter per second. That's the magnitude of the velocity, and we see it's almost the same as the vertical downward velocity, because of our x component is very small. Now we have solved for t, time, and velocity. We have left with the acceleration, so let's work on acceleration. So acceleration A, to find acceleration we can again solve, we have to solve two component, ax and ay. Now good thing we know that the velocity downward is constant. So acceleration y would be, by definition, derivative of vy v dt when vy is constant, which is negative 25 meter per second. So we know ay is 0. So since ay component is 0, we can use this ay. If we can connect ay with other variables, then we may be able to solve easily. So that will be our second equation to use. Second equation. Now, from definition, we know vy here is equals to the equation up here. So we can write ay, which is equals to 0, which is again equals to we can write 0 equals to if we get it from here, it will be 0.0515 x square vx. Now we know ay component is dvy over dt, and if we put that equation from previous slide and solve for that equation, we can take derivative. So what we'll get, we will get rid of the constant, which will be 0.15 the front. For x square, we'll get twice x. We have to follow the chain rule again because it's an x square and we're taking derivative with respect to t. So for x square, we'll get twice x, and for we will have multiplied by dx over dt, and we already had the vx. Similarly, on the second part, we will have 0.015 x square, and for if we take derivative of vx, it will be vx dvx dt. So this is a simple calculus when we have two parts of equation. When we have a multiplication of equation, we have to solve one part at a time, take derivative, and then the other part remains the same, and next time we'll keep the other part same, and then we'll take the derivative of the second part. So this is the ay component, and we know that this is equals to 0. So if we simplify, it becomes but before that, dx dt is also a vx. So this becomes 0.015 multiplied by 2, which is 0.03. And we'll have our x and vx whole square plus 0.015 x square. So if we take derivative of vx with respect to time, we know it's an acceleration, and this is x direction, so it will be ax. Now if we know the value of vx and distance of the plane, at current position, we found that it's 140.94, and then we found Vx as a 0.084. So 0.084, and here this one also value of x. So if we plug those values, we can get the value of the x component. So we get x component of the acceleration is a very small number, 1.001 into 10 to the power negative 4 meter per second square. Since the velocity in x direction Vx is small, we expect that Ax can be small. So if we look for the magnitude of the acceleration, which would be Ax whole square plus Ay whole square, which is 0. So we'll have only x square. So if we take square and square root, it will get the same thing, which this will be negative. We will get the same value. So the magnitude of the acceleration would be 1.001 into 10 to the power negative 4 meter per second square. So this is our final answer. So we have solved for the velocity, acceleration, and time. So now see, though the plane is moving downward at a constant speed, that's why our acceleration is pretty low. But it's moving downward at a speed downward speed of 25 meter per second square. So these are our answers. We'll in next video we'll solve another problem.